We're gonna have a second look at multithreading today, or more accurately, we're gonna have a look at some data structures that are especially helpful when multithreading. Technically also without it, but mostly just when using multithreading. And for the first one, let's think back on a problem I had in the last episode, where I had a class with an array internally, and I wanted to be sure that whenever I read the array to evaluate its data, it's not getting changed by another thread that's calling a different method that would change the content of that array. And in that case, I went a bit overboard and turned the normal array into an immutable array. That way I can always be sure that it's not changing. Of course, that was a bit overkill, but it works. There are other ways we can do that though, and other ways that are still more efficient than the lock. That would be the straightforward there. Let me give us an example to work with. Today is a bit more abstract than last time. No good examples directly. Let's have an int array, whatever. And let's say it has 10 items, this array. And then I'm gonna create another method. We're just gonna keep everything in the program class and just do everything static. That's good enough for today. No instance-based shenanigans necessary. And the first one, let's just do a void method. Read. This one is going through the array. I equals 0, I less than array.length and plus I. We're gonna sum up all the values. Sum plus equals array dot, not array, dot, just array I. That, and let's output that. Array has a sum of sum. Okay, so we're actually doing something with the output. And then, so just to make sure that I'm not changing the array itself and just the content, let's rename this actually. So that's the read method. And we're also gonna add another field. Static read only random. We're gonna use some randomness. And that's gonna be useful for the write method, correct? Autocomplete is right for once. And random.next, let's see, 0 array.length. Gonna first pick a random index, and then let's pick the value first. Value is equal to random.next. Let's go from 0 to 100. Meaning I should actually pick 101 here, because the random method works for minimum value inclusive, so 0 can be one of the values that the next method will spit out. This is the exclusive upper bound, so 101 is one larger than the highest value it can output, meaning this is able to output 100. And then we're just gonna change array index to value. And yeah, why not? Let's do another output. Changed index to, just so we know it happened, to value. Right, so let's just give that a try. First, let's call the write method and then the read method, and then do a console read key down here so we can actually see the console window. we changed the index of 9 to 44, and now the sum is 44, which makes sense. We started with all zeros. Let's call the write maybe twice. Index 1 was changed twice. So of course it's still the same sum. Let's just call the whole thing again, and 98, that is correct. So the methods work. But right now, the only reason we don't have any issues is because I'm calling them from one thread in sequence. The array access is always happening by the same thread, and only once the first write is done, the second write will attempt to write some other value or maybe overwrite the same one. And only then will we call the read method, which will iterate through the entire array and sum it up. Let's introduce some threads. With a D, not T. I mean, there are a thread, but let's actually make this an array. Threads equals new thread. Let's maybe go for a lower number, let's do 4. And then for I equals 0, threads length. Guess we're gonna change that later. And in here we're gonna do threads I equals new thread. We're just gonna add a new method in a moment. We're also gonna call the start method. And since we're doing this, we're also gonna do the because I feel like it. So once we end everything, so to speak, we'll join the threads and wait for everything to finish. And now the method we will call. These threads will all just read. Like this, -1. And then we're gonna do... No, actually, let's do it the other way around. Let's do it like this. And we start at 1. Makes more sense, maybe. And threads 0 becomes a new thread, right? That's correct. Also correct. What's with the autocorrect today? It's correct. It's guessing right. All right. So of the 4 threads, threads 1 through 3, highest index, will just run the read method, and the last one will run the write method. And actually that's not conducive to our test. Let's actually make 2 new methods here. Public static void read thread. This will get a while loop. We're gonna take care of that later. And this while loop will now read. And then thread.sleep for a bit. To take care of that, let's make another private. I'm just gonna add a bit of infrastructure to make the test a bit more interesting. Oh, active? Type reference true. True. Dear God, I can't type anymore. Okay, not that I ever was able to type, but and once we hit this, we're just gonna set active to false. Because it's a boolean, we don't really have to care about multi-threading. It's atomic anyway, so that's safe to use in here without any logs. Booleans are useful, especially for stuff like this. So as far as I can remember, random was also thread safe. So I can do random next in here, just to wait a random amount of time, anywhere between, let's say, 100 and 500 milliseconds. And then we're gonna copy the old thing and call this the write thread. It's gonna write, and it's also gonna wait 100 to 500. Read thread, write thread. All right. Here you can see the results. It's gonna constantly change the array in between. I'm just gonna hold in here. You can see it changes the array at certain times, and much more often it will just read the array. Because there are 3 threads that are trying to read the array and only one that's changing it. So of course it's way more likely that the thread that's reading it will be called. Even though they both wait the roughly same amount of time on average. And right now we're working with integer arrays, so we are still relatively safe. At least in terms of corrupt data. If this wasn't an int, not an atomic data type, but something more complex like for our class or maybe a bigger struct, then we might actually read the data wrong in here. We might read an individual item in the array while it's still being written and get completely corrupt data, potentially. But even without that, we have now a weird situation where I can be halfway through the array, summing up the values, and then an index that I already checked in here is now changed, and I still sum up the rest of the array as if that didn't happen. Or I read the first few array indices, then a value suddenly changes, and the later indices, and then I read it. In any case, the result of the read will sometimes be the array at the time the method starts, and sometimes the result we would get when the method finishes. It's right now not breaking, but the result that we output varies. It's not consistent. If a value that we already read changes, then we're basically looking at the old array, the one we saw when we started the method. And if the index is higher randomly in here, before we can see it, but while we're reading the loop, then we are effectively seeing the sum of the array at the time it's finished. It's still giving us a sum at a certain time of this array, but it's not clear at which point in time that was. And so we get inconsistent results over time. Not good. We want that to be clear. And so what we did last time was a loop. Lock. Static. Actually, this is a read only. Private static read only. We're gonna use a lock. Lock. Gonna use a new lock, like that. And what we can do in here now is we just put a lock around the entire method. Or we could put a lock around the method call write and read directly here. Either way works. And I'm just going to be a little bit lazy here and just write this out in here. Lock. That was the wrong key, like that. And we're going to duplicate that and put it down here. So access to the methods that change the array is now locked. So when the read method happens, we know until this method completes, we will not have any changes to the array. And we know while we are writing, nobody will attempt to read the array. This lock will prevent us from accessing the array at all times, which is good. This leaves us with a bit of a performance gap, maybe. Like, for the most part, this is fine. I mean, especially for my code here, this doesn't take any time, or this. And we're talking about some 10 elements, not 10 million or 10 billion elements. So this is pretty fast, no time loss really, and so the lock doesn't really mean much waiting. It's not like all the threads are suddenly waiting for a big task to finish for the next one to trigger, and so there's not really an issue where the multi-threading falls apart because they're effectively running in sequence again. But let's say these read and writes were taking a bit longer. What if they did actually need time to process? Just artificially increase the size here, just forcing them to take, let's say, 200 milliseconds. And here as well. So read and write now takes some time. Let's see the output. See, it's a bit slower now because read and write takes time. but at least there's no conflict. The results will be consistent. Thing is, if we look at our what's the term? Our balance of threads here. Why am I missing that word? I was thinking of that word a minute ago. The ratio. Ratio, that's it. The ratio of threads. We have 4 threads, one of which is changing the array. It is writing something. And the other 3 are only reading. They're not changing the array. So it would actually be perfectly fine for these 3 read threads to work simultaneously. They wouldn't need to lock the others out. They can just read all at the same time. The data will be perfectly fine. It's only when they interact with the write thread that you might have an issue. And while you can, of course, try to create your own logic for that, there's a simpler way. We don't use a normal lock for just standalone one thread at a time. We're gonna use what's called a ReaderWriterLock. And I'm using the slim variation here, but doesn't matter. Let's use the lock directly. ReaderWriterLock, 6 uppercase, like that. And we don't use that in a lock statement anymore. This works a bit differently. The ReaderWriterLock is a bit similar to semaphores and mutexes we had. We first have to request access through a method. And in my case, where's it? ReaderLock. Actually, okay, that's with a timeout. This would be like wait one method, something in mutex. I'm trying to get a lock with a timeout. If I use the slim variation, I have it a bit more straightforward. Trying to read lock. We have it. And I read lock. There it is. I was looking for the get, but now it was enter for the read writer. Same principle. I'm just calling this method to get access to the locked resource, which is just letting the thread work. And unlike the acquire at earlier, this one doesn't have a timeout specified, so it will wait indefinitely. But otherwise, it's the same principle. And to free access, I have to specifically call another method. This, okay, it was not release, it was exit read lock in this case. Okay, I don't remember these names in my head. Just to be clear, that's why I'm struggling right now. If I hadn't IntelliSense, I would always have to have some kind of documentation open. I mean, there's no reason to really remember every single detail, usually. Might be useful, but not necessary. What is necessary, however, is that we do call this method. If we did acquire access, if we did get the lock, we need to release it, otherwise we cause issues for other threads, because it's like we block access indefinitely. That's not good. So our good old friend, the try, comes into place. We aren't interested in catching the error though. We're just interested in making sure that no matter if an error happened or not, the exit read lock will get called. So we try to get access, which might itself fail. This can have an exception on its own, but in that case we didn't get the access, so that's fine. But if we do get access, we immediately go into the try block, so this code can work or it can fail, doesn't matter. Once this code failed or is finished, we will call the exit read lock and free resources again. Very important. With the lock statement that was taken care of by itself, similar to a using statement. You don't have to explicitly think of the disposing with a finally. These are not that integrated into the language. You have to take care of that yourself. Always exit the lock, insert the finally block when you enter them beforehand. Now down here we have the same structure, but we don't try to enter read lock. We try to explicitly enter the write lock. And same with the write lock though, we have to exit the write lock, free the resources again. And if you can't guess what this does, read locks just mean as soon as I'm entering the lock, as soon as we get access in our thread, we are blocking all other threads that are waiting to write. But we are allowing other blocks that are trying to read access. So we can have multiple threads in here at the same time. All threads that are trying to get a read lock will succeed and can get in here and execute their non-mutating calls. We can all read the array at the same time. We don't block each other. The write lock, however, if we try to enter the write lock now, it will block because there are still other threads reading the data. Once those threads all give up their read access, we are now only allowed to enter our code and start to write. And while we're in here and write, while we still have access to the write lock, the other reading threads will be blocked. They won't be able to enter this now. They're waiting for a read lock, but there's an active write going on, so they are blocked. Read-write lock means write blocks. Write locks are basically single-threaded. Only one thread can get write access at a time, but reading can happen to multiple threads. So it's like this asymmetric handling. One thread gets to write like a block normally, but reading can happen for as many threads as you want, as if there was no lock. Very useful for situations like this. If we look at the code, you can see there's still a bit of time gap between changing and reading, but the threads that read, that just output the data, basically happen in one go. They don't have to wait for one another. It's not like the method is get called and called again. They all just read at the same time, and that way speed up the entire process. Very useful structure for situations like this. Just a bit more to write out. You just have to remember to do that. Which was one of the reasons we didn't pick the lock last time. We used the immutable array to make absolutely sure that no one can trick us. I mean, we learned with reflections that you can still trick around, but in theory. That's the ReaderWriterLock. And more specifically right now the slim version, which is the same principle as the normal one, just a few different methods and some internals. Since we're working with multiple threads already, let's keep that trend up. Let's change these methods for now. I think I'm gonna keep the sleep. Don't need the ReaderWriterLock. Let's keep the rest intact. We wanna keep that. Let's actually go for just 4 normal threads for now. That. Red method. Whatever that is. So we have a couple of independent threads. And they have all their own code, which for us now is all the same method, but they might have all different methods with different code. But they all share that they have to do this one weird thing. as part of their normal routine. So all our threads are basically independent, but they all have to, at some point, do this one specific thing, for which we have conveniently one method that can all call. And actually we don't need the array anymore, let's just remove it. And this one thing might take some time. Actually, you know what? Let's add some indications to this stuff. Grad method, object. Oh, whatever. And this will get. Oh. In ID. Let's put it that way. Oh yeah, let's make this fancy. Let's make this fancy. For int I equals 0, I less than 20. Sounds like a good number. And do console.write. Console.write I. And is it actually? Yeah, that's good enough. And then do console write line like that. Okay, let's just see what it does with one thread and then add the others. That was the wrong. I didn't want I wanted ID. Okay, let's put it like that. Yep, that's correct. And now we add the delay because this takes a lot of time in computer time. Let's say each one here takes 50 milliseconds. And has to write that out. Okay, that works. Now let's add back the 4 threads. Again, they are basically independent, except they all do this one thing at some point or another in their lifetime, which takes a bit of time. And because they all have to do the same thing, we have to again kind of organize them, because this right now doesn't make any sense. This is basically corrupted data. We have to kind of organize them again. So back to the drawing board, we're gonna add another lock again, private static only lock, it's a new lock. Oh, let's just do it this way. Let's be quicker about it. And to make sure they don't all do it at the same time, I'm gonna put this in a lock, brackets like that. So only one thread may do stuff at a time. Okay, this way the data is no longer corrupt, but actually looks neat and tidy. Not really an issue, right? This is fine, right? Let's say we increase the time a bit. It's not 50, it's this time 100. But also these threads don't have to call to stuff all that often. So maybe this is every 5 to 15 seconds. At this point, add those in there. Quick reminder if you forgot, underscore can be used as a separator for every thousands. Or basically you can use it as a separator anywhere in your numbers. Like C# simply ignores the underscores in those integer numbers, and we use them as thousands separator. So 5,000, 15,000, 5 seconds to 15 seconds. That's how long these, actually that might be a bit too much. Let's go for 10. So all these threads are every 5 to 10 seconds gonna call this method do stuff, which itself is gonna take to, let's increase it actually. Let's go for 400 maybe. Takes a bit of time. It's a complicated method. And then the next one, actually, you know what? This is a bit too slow for me. I'm just gonna speed it up back to 100. Whatever. They're all gonna do their thing. And looks fine, right? Oh, what was that? What was that? What is this? Suddenly, for a moment, nothing happened. No, looks fine again, looks fine again. Everything is fine. Ooh, again, a bit of delay. What's going on here? Just gonna abort it. Big break. Actually, we should add another one in here, just to make things end a bit earlier. Add active. Active in here as well. Okay, just so we can abort earlier safely. Well, these threads are all gonna try to access do stuff, and they're all gonna wait for this do stuff to finish its thing, and then they're gonna do their own stuff, which takes time again, before they can go back and try to do stuff again. I think it's because they all want to do stuff, basically at the same time, at least in the beginning. They have to wait not only on the method, they have to wait on the method call of the other threads as well. All 4 threads in the beginning will try to do stuff. One thread will succeed, which will take it about 2 seconds to finish, and the other threads have to wait. They have to wait first 2 seconds for the first thread, then another 2 seconds for the second, then another 2 seconds for the third. So the 4th thread may have to wait 6 whole seconds before they even get a chance to start. And of course, the chances are that by that time, one of the earlier threads is now back in the race and also tries to do stuff again. But it could also be that none of the threads are ready to do stuff again, and we're not doing anything. So, purely based on timing and random chance, and your program based on user inputs and whatnot, you may have times where all threads are currently blocked. None can actually do their own stuff because they all work to do this one thing all at the same time. And then in other times, nothing really happens and no thread is trying to actually do anything with the resources available. So we have a sudden performance spike, so to speak, where all the threads are trying to do the same thing and we have lag because no one can actually do work. While at other times, no one is actually doing anything. And we're wasting available processor time. You might not see it as exaggerated right now, but that is basically what's happening here. Resources are not used smartly. And one of the ways we could optimize this is by having another thread. Let's gonna call it very creatively processor, and we're gonna add a new method. Static void process, whatever, like that. Process, and we're gonna process.start, and then we're also gonna do process.join, because I like to have everything clean. And now we're gonna do one small change. We're gonna add a queue. Oh, yeah, let's go call it queue, whatever. It's fine. We'll name it with a lowercase u. And instead of calling do stuff in here, instead of actually doing the thing we need to do, we can, at least in our case, just go queue.enqueue, and then we're gonna do the value we actually want to have in there. So we're not actually doing the work on our thread ourselves, we're just adding it to a queue of work to do. And process also have a loop. And process will just queue.try dq. Gonna see if there's anything in there. And call it, let's call it ID again. And if there is an item in there and we try it and we successfully got that out, actually that's not a nullable, it's just an int. Sorry program. Then we're gonna call do stuff with ID. And if not, we're just gonna repeat. Though that's a bit of a waste, so if we didn't find stuff because nobody added anything, we're just gonna sleep for a bit. Just wait for a second, and then we're gonna back to the top of the loop. We check, is there anything in the queue? If so, process it. If not, just wait for a second again to see if there's a new item. We're not gonna change do stuff at all. And this code technically works, but we have again the issue of queue. Similar to the array in the beginning, we are now reading the data in one thread and writing in several others this time. And we have to make sure that things don't break. The queue can actually kinda get wrecked in the process. It's not exactly thread safe. So we have to make sure that access to the queue is made thread safe, which we could do through another lock again, just for the queue. Right, every time we access the queue, we do that inside a lock, down here as well. Let's just do that. Let's put that out on the variable. Found item like that. And I think that's unnecessary. Put that in there. Let's put that on here and then lock. Seems about right. Because we put it in a lock, we have to put the variables we use outside of the scope. Technically, keep in mind, this is still having brackets. This is internal scope, so everything we do inside here would leave the context once we hit this bracket. I'm just hiding the brackets because we don't need them. It's a one-liner, but it's still its own scope. So I have to declare the variables outside of the scope, so we can use them down here. It's a bit cumbersome, but it works. So now the queue is safe, but it's only the access to the queue that we have to lock, which is extremely quick. And all the active work, all the stuff that takes time, is handled either by the threads themselves for their own unique stuff, or by this one special thread that's taking care of the do stuff. And conveniently, because there's only one thread doing this process, we don't have to lock access to do stuff. This thread, this one thread, is the only one that will access the method. So it is inherently safe, even without any locking necessary, which is good. So let's try to execute this one. All the other 4 threads filled the queue with their items and just continued on their own. And then once they get back again, they just add an item to the queue. So for the most part, we don't get any breaks in between. We use the full time to process items in the queue. And the different threads don't have to wait for do stuff to finish, which is quite convenient since in our case at least, they don't need the result. That's of course a requirement. If they need the feedback, if this do stuff method would return anything they need for their own processing, then this throws the entire concept of the window, but otherwise, very convenient. You just have a bunch of threads that do their own thing and throw in work items for a separate thread to take care of in a loop. This one thread is purely dedicated to this one specific job, and it does the collective work of a bunch of other threads that do their own thing. This kind of structure is quite common. You have several threads that do completely different things, but there are some resources that they all need to access in some way. And instead of doing the jobs themselves, there are dedicated threads to take care of that. And in our case, that's this one thread. It's one way to make the entire computer a bit more efficient. We use the time more efficiently. As long as there's any work, this process will take care of that. And if at some point there's really no new item, only then will this thread run empty. This highlights two different things that could be a bit more optimized. At least I was trying to highlight two things. The first one is the queue itself. Writing all of this out because of thread-safe queue access. I'm too lazy for that. And luckily, the C# team or .NET team agrees. So in the system namespace, there is another type we can use, and that's the concurrent queue, which is basically just a queue, like you know it. But concurrent queue is inherently thread safe. So you can see I can use queue just as before, but I don't need to have the lock in here. Let's put that back in the one-liner, and then we can also just drop this back in here. Get our old code, simplify it a bit, and we can use this. Concurrent queue internally makes sure the data doesn't get corrupt when multiple threads try to access the data. If you add an item, it is safely in there without getting corrupted. When you try to read an item, you either get an item or you don't. And if you do both at the same time, well, it depends a bit on some random factors internally, which thread gets blocked and waits for the other to finish and whatnot. But concurrent queue, thread safe to use in multiple threads, no need to add any locking mechanisms yourselves. And concurrent queue is not the only type you have. There's also concurrent stack, of course, the counterpart, queue and stack. First in, first out, first in, last out. We also have concurrent bag. Not sure if we talked about bag, but think of a collection like a list, except items don't have an order. It's more like a set. I think it's like but it's hard to formulate. It's a bit like an overlap between set and list, but basically it's just you can put items in there and you get items back out, but there's no order. If you try to read an item from back it out, it might be the last item you put in there or the first item or some other item in between, and there's no order in there, but it holds the items nonetheless. Not really used for me. I haven't used concurrent back before, I think. For me, the order is usually quite important, so it's either a stack or a queue. And if I have some really weird requirements, I always fall back to just having a normal data structure that's not thread safe and just add a lock around it. And last but not least, concurrent dictionary, which is also just normal dictionary that happens to be thread safe. And now with our queue, we can drop the lock. We don't need that anymore. We can outsource our work into one specific thread. We use processor time more efficiently. The threads can work without worrying about the work down here. Don't have to wait for that. Just everything is a bit more smooth. Except for the time when there really is no work. Let's say we up this to 10 seconds to 15 seconds. Well, looks good so far. Ah. Okay, suddenly no more work. And some work again. Good, good. That was just a small hiccup. Everything is fine. Everything is fine. Oh. So we can run into a situation where we don't have any work, which is normal. But in that time span, we're kind of wasting time by doing this down here. If there's no work to do, this entire loop just repeats endlessly, doing nothing but just waiting for 1 second and then trying again, which is wasteful on one hand, and also means reaction time is slowed down. Let's say we make a DQ, essentially at the same time one of the threads puts an item into the queue. And just purely based on timing or some internal shenanigans, despite being almost simultaneously, the DQ resulted in a false, we didn't find the item. So despite an item being in the queue, we are waiting an entire second and only then trying again. We're wasting an entire second where we could have already started working and be halfway done by now. We don't want to just statically wait a second to try again. If there's no work to do, we just don't want to do anything, period. But as soon as there's work to do, we want to immediately start, as fast as possible. You already know a structure that would allow us to do that. We could use a wait handle, because a reset event, manual reset event or auto reset event, and that way add some code in here that would not only add an item to the queue, but also trigger the event, which would cause this code down here to suddenly jump into action and start the loop. That's one way to do it. But because that kind of thing is, again, common enough, there's another structure in the standard language libraries that includes this event that reacts as soon as there's an item. And this special structure is also another collection like our queue. Yep. It's a blocking collection. Now, blocking collection itself is a more abstract class that can internally be different data structures. So it really is just a collection. There's not a very specific data structure associated with it. This is not a list. Not directly. I think the default is a list, but it can be other things as well. And we can determine what data structure this actually is, like determining that this is supposed to be a queue by providing it a queue, specifically a concurrent queue. If I pass on a concurrent queue, the one we just learned about, this blocking collection will act as a queue. If I provide it with a concurrent stack, this blocking collection will act as a stack. Or I can give it a concurrent bag and then it will just act like a bag. But by providing a specific concurrent collection, I'm determining what this behavior will be. Because it's not fixed to a queue anymore, it doesn't have the method enqueue. It does have an add method though. You can add the item, which is for a queue, an enqueue. For a stack, it would be a push. But it's generally the same result. And it also doesn't have a try DQ because it's not a queue anymore. It does have a try take. In that case, I think in this case it's a null. No, what was it? No, try it. Try take. That's why it didn't work. So, try take would be try pop or a try DQ for a queue, but otherwise behave the same. We can let this run. This is technically valid code, does its job, but we wanted something special here. Blocking collections have this cool little feature that we can rephrase this. Let's just show it. There's a method getConsumingEnumerable, which will give you an enumerable that you can just iterate through. Like that. But this enumerable itself will only give you an item if there is one. As long as the queue is empty and no more items exist, this will simply block your current thread. It will wait. And the moment this queue gets filled with an item anywhere, this part of our code will get a signal that wakes it up and spit out the item it just got, or one of the items it has. And when it returns to the top of the loop to get the next item and it notices that was it, there is no more item, it will wait again until adding an item at some point will wake it up again, and it continues. So we can do stuff in here already, like that, and don't have to do anything else. Though we do have to take care of the closing now a bit differently. I'm just iterating through this thing. We just get an enumerable. Right? It's just a standard enumerable as far as you are concerned. It's only that getting the items, move next. Get a numerator and then move next can take a bit of time. It will wait until an item is ready. Let's return this, but to stop the system that will just permanently block the current thread and wait for an item to come in, we have to tell this queue that we're done. Wherever someone is waiting for items to come in, they can stop. And at the same time, we can also block any more further attempts to add stuff. We can do that with queue.completeAdding. QCompleteAdding will internally set a flag in this queue that will prevent us from adding anything anymore, and at the same time will also tell this consuming enumerable to just complete, to finish, the moment it read the last item. So once we set complete adding, it doesn't mean everything stops, it just means we completed the adding part. We block any further attempts to add stuff. But the queue will still finish reading its content in this loop until it's completely empty. And once it's empty, it will see that queue dot is adding completed, which will be true because we called the method in here, and then it will end the loop and exit. Which gives us an interesting little problem to solve in here, potentially. Let's just basically end it. And I didn't manage to provoke it. What did I do wrong? Where did I go wrong? Okay, let's just do it again. So I basically gave the signal for the stop. I completed adding. Let's wait for 15 seconds. There we go. So that worked. We didn't get an error. Okay, too bad. I'm not trying to provoke it now again. But instead of add, we can also just do... Now I will try add, like that. So add will throw an exception, but try add will just give you false if it didn't work. So if you plan on stopping, then this is not necessarily the best way to do it. Yeah, complete adding will prevent you from adding anything more, and it will prevent this queue from just, or the consume enumerable from blocking once the queue is empty. By the way, since we're soon starting to look into more abstract use of programming instead of individual language features and libraries, there's a pattern, consumer producer pattern, and this is the consumer part. This thread is a consumer, it's a consuming enumerable, and this method here of the 4 other threads would be a producer. It produces data in this thread that is consumed in this thread. And it's just a way to make code a bit more efficient. For example, we use a logging library that would, in the regular code, would just call a method to add a log message. But this log is processed in a series of different threads that have some special properties that take care of the incoming logs and process them further, try to analyze them, add proper messages, format them, output them, I/O and all that, which takes a bit of time. So outsourcing that from the main code to some parallel code is making the whole thing just a bit more efficient. That's one example. Or network code, for example. Very simple network code, you write a multiplayer system and you want to send your player inputs to the other players. Well, you don't want to send a message to all the other players that you hit the up key to move forward and then wait for the feedback that yes, the message arrived, thank you. You want to hit the up key and then just move forward on your own, and the sending the stuff to the other players is happening in the background thread somewhere else. And maybe you have some reactions when that failed, but you don't block the entire game for that. So it's just a very simple principle, and this is a very simple example of how you can use that. And honestly, that's it for today. It's a very short one. Just wanted to show them off because after last time there may have been some open questions, and I thought these are some pretty cool structures. We had the ReaderWriteLock, which is a very useful locking mechanism for cases like last time, where you have a series of threads that need to read, which can all, or actually it's not just reading and writing, it's just anywhere where you have a series of threads that are safe to interact with a certain part of your code in parallel without any conflicts, while also having some rarer parts of code or threads that actually have to engage with that data in a conflicting way. So a bunch of threads need to access the data, but they can all they can access the code safely. And maybe 1 or 2 other threads that change that data that have to log out the others. And the read-write lock is just, these threads can all do it at the same time, no problems, no conflicts. If this thread tries to access, please block any other access. They get exclusive access, the others all share the access. And reading, writing is just a very common thing for that. And the next part was the concurrent queue, or concurrent bag, concurrent stack, just a thread-safe data structure, inherently thread-safe, which is just more convenient than adding a locking mechanism on your own. Because that means you have to at least share the lock. And in the end, you could create your own data structure for that, but even then there might be issues. For example, if you imagine just having a normal queue and adding a lock and just sharing those two around with maybe a struct, simple, straightforward, there could still be issues when accessing the queue at the same time and copying the reference out, and there are lots of shenanigans you can do. Concurrent queue, one single type, thread safe inherently, don't have to worry about anyone accidentally messing with that, it just works. And then based on the concurrent data structures, we have blocking collections, which can be wrappers around a concurrent data structure that allow you to do this cool thing, the consuming enumerable, which allows you to effectively create nice little self-contained producer-consumer pattern. I don't really have a use other than cases like this. I'm not sure what else to do with it, but it's very cool system. I should mention you can, in theory, limit the size of these. We earlier had just talked about wasting processing time that is available when there's nothing to do. The opposite is, of course, also a factor you might have to consider. If these threads are very, very fast, but this process is very slow, that means this queue is constantly getting filled up and it's getting bigger and bigger and bigger with a larger backlog of things to do. And for that case, maybe you want to set, first of all, some kind of process in motion that starts a second thread that uses this consuming enumerable to read data. You can use multiple consuming enumerables at the same time. So I can have two threads that do process. That's perfectly fine. They don't block each other. It's already thread safe. You can do multiple threads that do the consuming enumerable and process your queue, and to speed up the process at which you work down items. And then once the queue is nearly empty again, you can turn off some of those threads to save resources until you hit the upper threshold again. And to make sure you never hit some very important limit, you can also set an upper limit for your queue with this blocking collection, at which point the add method will itself wait. So when the queue gets too full, you can set it so that this add in our thread will actually block itself until this queue gets below that threshold, at which point it will continue our code in here. So also pretty useful. Maybe you need that at some point. Yeah, that's actually it. Thanks for joining. See you next time.